So, we've been talking a lot about nuclear reactions and radioactive decay. And so we've got radioactive decay happening. What's changing about our atom?
We've been changing the nucleus.
We've been changing the nucleus.
Yeah.
And so remember, our nucleus is going to tell us what atoms we have. So it's going to look a little bit like we lied to you in the beginning of the year, where we had chemical reactions, and your chemical reactions could always only have the same elements on each side.
Yeah, we always had to end up with what we started.
Because that was for standard chemical reactions. Those don't change your atoms. We're doing nuclear reactions now. Our atoms do change. However, the law of conservation of mass still applies.
Okay.
So our numbers still have to add up on both sides. So it's actually pretty simple.
Okay.
We need to know what's going on with our nucleus, so we need to review nuclear notation. So our nuclear notation tells us a couple of things. The first thing it tells us is our element symbol. And where do we find our element symbol?
Periodic table.
Periodic table. So it's just whatever letters are on the periodic table.
Okay.
It also tells us our atomic number, which is our number of protons, which we also find.
That's also on the periodic table.
Right. And if we change our atomic number, what else changes?
The atom changes, so that means the symbol will have to
Right,
change.
so our actual element will change. But our top number is the part that can change without changing our atom. The top number tells us our mass number, which is our protons plus our neutrons. Remember, our neutrons can change.
Because if we change our neutrons, we have, I remember this word, isotopes.
We have isotopes. All right, so this number can change. This number can't without changing our atom. Both of them are going to change when we balance nuclear equations.
Okay.
So let's look at some possible nuclear equations. So one of the things we can do is an alpha decay, and we should remember that an alpha particle is what?
Alpha particle, the symbol was, we say the symbol is helium because it was 2 protons, so atomic number 2.
Okay.
And mass number 4.
Right. So we've got a mass of 4, 2 protons, which makes it helium. So that if it's an alpha decay, that means that has to be one of our products.
Okay.
So now we get into the actual balancing part. Law of conservation of mass says what?
We have to have the same amount of matter on both sides. So if we started with that much matter, we have to end with that much matter.
Right. So we see that we started off with a mass of 238. And we've accounted for a mass of 4.
So that means I should have 238 minus 4, which is 234.
Right. Because the total mass has to be the same on both sides.
Okay.
So if my mass has changed to 234 because 4 of it went to my helium.
So we're going to have to do the same thing with the atomic number.
Right, because your total number of protons has to stay the same. Your protons can't just disappear.
Okay.
So if I had 92 protons on this side, and I've got 2 protons so far on that side.
We need to have 90 more. So that's our atomic number.
So our total mass on our reactant side is 238. Our total mass on our product side is 238. Our total number of protons on our reactant side is 92. Our total protons on our product side.
And we can use the atomic number to figure out what the symbol is.
Right, so we look up over on our periodic table, we try and find atomic number 90.
That's way at the bottom. TH.
Thorium. Thorium.
By the hammer of thorium. Sorry.
Yep, no Mjolnir involved in this one.
Too bad.
All right, so that's all we do. We make sure our totals match up, and we find our symbol.
Okay, that is actually really easy.
Right, so why don't you try this next one on your own? So we're trying to figure out the alpha decay again, because we're going to make an alpha particle for radium.
So I'm going to go ahead and start with the alpha particle. So the mass number was 4, the atomic number was 2, and my symbol is He.
Right, and remember we can also, if we want to, write it like an alpha, like the Greek letter. So if you see that, this is also an alpha.
So either the alpha or an He. It can be
right. So it's a little fishy looking little A.
Okay.
Sometimes. All right. But so we have a mass of 4, 2 protons.
All right. So I need to have 220, a massive number of 222 on both sides. So 222.4 is 2
222 what?
Plus 4? Minus 4.
Minus 4 because we want the total to be the same.
Okay, right. So 222 minus 4 is 218.
Okay.
And I got to do the same thing with the atomic number. So I've got 88 on one side that means I need to have 86.
Mm-hmm.
Plus 2 gives me my 88. Okay. So that means my atomic number is 86. So I have radon.
Mm-hmm.
Rn.
Oh, there we go.
Wow, that is remarkably easy.
Yeah.
Okay.
All right. So let's try something a little bit different. So over here, we've got beta decay.
Okay.
And so if you think back, we were talking about beta particles. What were our beta particles?
Beta particles were like electrons.
Were our electrons.
Yeah. So
our symbol was just an E.
Yeah. And we said that the mass number is 0.
Mm-hmm. They don't have enough mass to worry about. Okay.
And
so do electrons have any protons?
no.
No, but they do have a charge. What's
They're
their charge?
negatively charged.
Right.
So then
So instead of a number of protons, we have our -1 charge because our charges have to add up on both sides too.
okay, right.
So that's going to make our math just slightly different on this. So we have a mass. Oh, I lost my electron. All right. So our mass on our reactant side is 131. Mass so far on my product side is 0.
So that means the missing mass is 131.
Yeah.
To make it the same on both sides.
Okay? This part's where it gets a little bit different. My atomic number is 53, so my total charge is 53.
But the bottom numbers have to be the same on both sides.
The total of the bottom numbers has to be the same on both sides. So last slide, we subtracted. Here we're going to have 53.
So now we're going to have to add it.
Because it's minus a negative.
Yeah, so it's got to be 54.
Mm-hmm.
So when I put 54 and minus 1 together, it gives us 53.
Right.
All right.
And so 54 on the periodic table is?
Xenon.
Xenon.
Xe.
Also not a warrior princess.
No, too bad.
All right.
So really, the same. We still have to make sure that the number on top and the numbers on bottom are the same.
Mm-hmm.
That's the main focus. Just how we do it was a little bit different.
Yeah.
Okay.
So same
All
thing
right.
again.
So then on the bottom one, let's do our beta particles.
Mm-hmm.
So it's 0, -1 with an E.
Okay.
So-
Remember, this also will sometimes show up as that B with a long tail because that's the Greek letter beta.
Okay.
All right.
So the other side, let's see, 14 on top, so they can be the same. And I need to add those two numbers together, so it needs to be 7.
Mm-hmm.
And then atomic number 7 is nitrogen, N.
There you go.
All right, that's really good.
Mm-hmm. And the funny looking stuff on the end says that we give off energy in the form of gamma rays on both of them too.
Oh.
But we don't have to account for it because both are numbers.
Well, yeah, because they're 0 and 0. Okay.
All right, let's try our next type. Now we have positron emission. And a positron is what it shows down here.
That was kind of like the electron, but it's the opposite of an electron, so it's a +1.
Right, so it's still going to have a mass of 0. So let's go ahead and fill in our positron. It's got a mass of 0, a +1 charge, and we can write it as an E or a beta. Either is fine.
So top number on the empty space has got to be 23. And we want to make sure altogether it's 12 and 12 on both sides, so 11.
Okay.
Because then 11 plus 1 is 12. All
Right.
right, atomic number 11 is sodium, Na.
There we go.
Wow, this is super easy.
Yeah, it really is.
So we can do it again. The positron, it's 0 on top, -1 on the bottom.
Mm-hmm. Wait, what charge does the
-1. Beta particles.
What charge does the positron have?
I keep saying it positive.
Yes.
A beta particle is -1.
Right.
Positron, +1. Positron, positive. Okay.
Yeah.
I got it.
So top numbers are the easy parts.
50 on the other side. On the bottom, I want to do 25 minus 1, which is 24. Atomic number 24 is chromium. Cr.
There we go.
Okay. Okay.
So,
I
and
can
this
get
is
behind this.
positron emission because it's giving off
A
positron.
A positive particle.
There we go. All right. Let's try our next one. So our next one gets a little bit different, because now instead of giving off a particle, we're picking up a particle.
We're
Because capturing it.
Okay.
All right, so it's an electron capture, and remember the electrons are written like this. We've seen these before.
So we want to put that in on the reactant side.
Right, so it's 0, minus 1, E.
But the same rules still apply. We want to have the top numbers to be the same. So 239 on top. All right. 96 minus 1 is 95, right? Because then I'll get 95 on both sides. Atomic number 95 is AM.
All right.
Americium, right?
Yep.
That's how you say it?
Used in smoke detectors, by the way.
Ah, yes, that's right.
All right. Same thing on the bottom.
Okay, so we put our electron. 0 on top, -1 on the bottom.
And it's a reactant because it's electron capture.
Right.
Okay.
Okay, so the top numbers are easy. That stays 81. And then we got 36 minus 1 is 35, which is bromine.
Okay.
Oh, okay. We got one more?
Yep. So now we want to deal with neutrons. And so neutrons are neutrally charged. They have a charge of 0.
Right.
And they have a mass of 1. So this is our neutron, which is already filled in for you.
But law of conservation of mass still applies.
Our math doesn't change at all.
So, okay, that means the top numbers we've got. Let's see. Okay, so
what's happening here, it gets actually a little teeny bit more complicated because we've got these two particles coming together and we're getting two particles out of it. So we've got to pay a little more attention to our numbers.
Okay, so I've got 253 plus 4. So on the reactant side, we have 257.
Okay.
So that means on the product side, we also want 257.
And so far we've got 1.
So that means the other number needs to be 256.
Okay.
Okay, so that means we want to do the same thing. We've got 99 plus 2 is 101.
And we want 101 total on the other side. Do we have anything for our charge on the other side?
No, so we can just put 101. And 101 is, the symbol's MD.
Mendelevium, I think. MD is the important part.
Okay.
Fairly certain it's Mendelevium.
Okay.
All right, so still, the math hasn't changed.
Yeah, nothing's changed. All right, so then if we take a look at the bottom one, we've got 9 plus 4 on top, which is 13. So we want 13 on both sides. We've already got 1 with the neutron, so that means it's 12.
Yep.
4 and 2 is 6. That means we want 6 on the other side. 6 plus 0, and then that would give us carbon.
Yeah. There we go.
Oh, okay.
See, regardless of which type is going on, it's the same math the whole time. You make sure your top numbers and your bottom numbers add up on both sides. And then which type of reaction it is just depends on what your
What
particles
particle
are.
is going on.
So if you've got, so this involves neutrons, this one's technically kind of alpha capture. If we have electrons being picked up, it's electron capture.
If we have a positive electron, a positron, then it's positron emission.
Yep.
Beta particles, which are they say they look like the electrons.
Right, that's going to give off an electron if it's beta decay.
And then alpha decay is we're giving off an alpha particle, which is that 4 on top, 2 on the bottom, and either the HE
Or the little
fishy looking thing.
All right, so that's what we need to do on this.
I like it.